I'm Lisa, and we're going to be talking about MRI and the atom and how MRI works. It's kind of rudimentary, very basic, so let's see if we can do it together. Now, every now and then, I may have to pause the video, so just bear with me. Let's first start talking about the atom itself. Basically, we have protons, which have a positive charge, neutrons with a zero or no charge, and electrons with a negative charge. Now this is a Bohr diagram, which sort of graphically represents these three. You've got electrons that circle the nucleus. The nucleus has your protons and your neutrons. Now your atomic number is the number of protons. This gives the atom its identity. For example, a hydrogen atom has one proton. The atomic mass is the number of protons plus the number of neutrons. When the number of protons does not equal the number of neutrons, you end up with what's called an isotope. When the number of electrons does not equal the number of protons, you end up with an ion. Now, usually, most of the atoms, they're all equal. The electrons equal the number of protons, equal the number of neutrons. So you can see when there are differences, it makes a different atom. For example, an ion will carry a charge because you remember the electron is negative, the proton is positive. So when they don't equal, you have more than one or the other, which gives you a charge. Now remember we talked about mass number. When the number of neutrons does not equal the number of protons, you end up with an odd mass number because remember the mass number was protons plus neutrons. Now why is that important? When you have each of these, let's go back for a moment. Neutrons, protons, and electrons all spin. Usually, they cancel each other out. One spins one direction, one spins another direction, and they cancel out. When they don't, because they're unequal, now, if they do not spin equally and have a net spin, one way or the other, which is called angular momentum. Now, these particular atoms are what we use in MRI, and they're called MR active nuclei because they have this angular momentum or spin. Now, why is the spin important? Let's talk to Mr. Michael Faraday. Now, he found the law of electromagnetic induction. What does that mean? Remember, we're looking at ions to where you have a charge because there are either more electrons or more protons. So what Michael Faraday found was that if you have motion, which we do because the atoms are spinning, remember angular momentum? They can have magnetism and they have a charge. What he found was that if you have any two of these three, the third is automatically induced. So what does that mean? Remember MRI active nuclei? We know they have a charge. We've already said that because the protons and electrons aren't the same. They have a spin. Remember angular momentum? So they have two of the three, which means the third magnetic moment or magnetism is automatically induced, which means they align with the external magnetic field, just like a magnet. Now let's pause for a second and talk about the atom that MRI uses most. The hydrogen isotope. Remember isotopes? They don't have the same numbers? Well, the isotope in hydrogen that clinical MRI uses is called protonium. Now, why do we use hydrogen? It's the most abundant atom in the body, and it also has a very large magnetic moment. Now remember the law of electromagnetism? It basically says, remember Michael Faraday? Charged particles, when they move, they create a magnetic field, and it acts as a magnet. So basically, when the hydrogen atom is moving, it's becoming its own little magnet. Now, the hydrogen atom is charged and is moving. Remember the laws? So now we know it is a magnet. Let's talk about magnets for a second. Magnets all have a north and a south pole. They repel each other. These are represented in our field as a magnetic moment. Now, this magnetic moment, where the north and south poles are represented, has a vector property, and those properties are size, direction, and an arrow. So what does that mean? Here's happy little hydrogen atom. Basically, here he is. This is his arrow. Now that arrow represents your magnetic moment. You have a direction, and you also have the size of that magnetic moment. Now you're asking yourself, why do I care? Why is this important? Well, it's important to understand alignment with your magnetic moments. Now, alignment is explained by two theories. The first theory is the classical theory. The second theory is the quantum theory. We're going to kind of combine both, but let's first talk about each one separately. Now, usually, most atoms are kind of chaotic, sort of like Grand Central Station, all over, everywhere, moving in different directions, different spaces, all over the place. Now, let's change up the mix. Let's add an external magnetic field, which is going to be represented from here on out by B small o. When you add that external magnetic field, which is represented by this arrow, now you're seeing in the classical theory that you have them aligned, all the atoms aligned parallel, which go along with the strength of the BO, or anti-parallel. They oppose BO, which means they're going in the opposite directions. They're pointing down, which is opposite of the BO. Now let's talk quantum theory. Now quantum theory, thanks to Max Planck, uses bundles of energy or quanta. Now what it says is that when you add your external magnetic force, BO, in this direction, you have some of the nucleus lining up parallel or going in the same direction as BO. Now these are called low energy nuclei. They spin up and they're considered parallel. Some of the guys don't go along with that. They are anti-parallel. They go down. This basically means that these nuclei have enough strength to be able to oppose the external magnetic force and point away. These are called anti-parallel, spin down, and they are high energy because they have enough energy to oppose this magnetic force. Now, in both theories, there are usually more parallel or spin up nuclei than there are anti-parallel or spin down. The alignment is affected, whether or not they spin up, spin down, parallel, anti-parallel, that's affected by the strength of the external magnetic field, and it's also by the thermal energy of the nucleus itself. Now, what all does that mean? Basically, what you're looking at is a net magnetic vector, which we're going to be looking at as called the NMV. Basically, what it's saying is for each anti-parallel spin down, there is a parallel spin up. So they typically cancel each other out because remember, there are more spin up parallel than there are spin down. As I just said, as there's usually more, they cancel each other out. What's left over is the net magnetic vector, or NMV. Now, the net magnetic vector can be affected. If the external magnetic field, the BO, increases, there are fewer nuclei that can oppose BO. So you won't have as many anti-parallel or spin down. So after they cancel each other out, there are still more parallel nuclei than anti-parallel. And that means you have a weaker than left over than with a weaker external magnetic field. Now, what does that mean? Let me show you. Basically, when you have a weak external magnetic field, which is BO right here, these are your spin up parallels. These are your spin down anti-parallels. You can see they cancel each other out. Now, with a weak magnetic field, you have about as many of one as the other. You have enough that can oppose it versus enough that are not opposing it. And you're going to have very few left over. This is your net magnetic vector, and it's pointing up. Now, what if you use a strong magnetic field? Basically, the opposite happens. Because it's a strong field, you don't have as many atoms that can oppose that magnetic field. So you have more spin ups. What does this do? After you cancel each other out, you have more spin up left. And now that's your magnetic vector in the direction of your spin up. Now let's break for a second and talk about something a little bit different. Precession. Now when you have an external magnetic field, it actually causes a wobble in the magnetic moment that pulls the magnetic moment off center. Now this wobble is called precession. Now why is that important? To further talk about precession though, we need to break for a moment and talk about the precessional path. Now the precessional path is the magnetic moment's circular path around your external magnetic force. When you have a path, you're also going to have a precessional frequency. Now, the precessional frequency is the speed of the wobble around your external magnetic force. And this is done in megahertz. So basically, when you have precession, you're going to have a path and you're going to have a speed. Okay, so let's talk about the precessional path and the precessional frequency. This is going to be a real silly little way to demonstrate it, but it's pretty easy to understand. Simple orange. Now typically, what you're going to have, this is your vector. It's kind of off center a little bit, but it usually is going to go straight. When you add in an external magnetic force, there's your wobble. Now see how it's no longer straight? Now when you have this electromagnetic force or magnetic force coming in, you're going to have your spin. Now that's how it's spinning. Now you see the path that those little yellow dots are making? That's your precessional path. The speed, it can go slower or it can go a lot faster. That is your precessional frequency. Now again, it's a pretty simplistic way of seeing it, but it can kind of help you understand how you've got your different little wobble here. It's not straight, it's off kilter, and you've got your path. Okay? So now you're asking yourself, what does all this have to do with MRI again? Well, each atom has its own precessional frequency, its own path. So the precessional frequency is in the speed of its spins. So how do we pick out the speed of its spin versus everybody else? Because all the body does have a precessional frequency. Well, since we know that each nuclei has its own spin or precessional frequency, we know the rate of the spins for that particular atom. We can pick out that particular atom using the Larmor equation. And that finds the particular frequency that each atom has, because every one has its own for that particular atom. Now, how do we do that? First off, let's remember that MRI uses the hydrogen atom. So how do we pick out just the hydrogen atom? Using the Larmor equation. Well, what's the Larmor equation? Basically, the Larmor equation is your precessional frequency is what we're looking for to pick out that particular atom specifically. The strength of the external magnetic force times the gyromagnetic ratio. Now, the gyromagnetic ratio is constant for each atom, and for hydrogen in particular is 42.57 megahertz per Tesla. So what this does is, depending on the strength of your magnet, for example, a 0.5 Tesla, 1.5 Tesla, or a 3 Tesla magnet, you multiply that by your gyromagnetic ratio, and then you have the precessional frequency specific for hydrogen, which is what we're trying to find using MRI. So let's kind of review as all this is starting to sort of ball up. First thing, remember the MRI active nuclei, they have a charge, it has a spin, which is it automatically acquires a magnetic moment. So they align with the external magnetic field. Remember our happy little hydrogen atom with its direction, its arrow, and its size, which is the magnetic moment? You take all those magnetic moments together, remember our quantum theory. You have the spin up, parallel, the spin down, anti-parallel. Since you have your magnetic field, they do cancel each other out, remember, to get your net magnetic vector. When you have a net magnetic vector, you also have precision, because when you add that external magnetic field, you get the wobble. When you have your wobble and you have your spin, now you have your precessional path and your precessional frequency, which is the rate or the speed of those spins. Now, because you're looking for a specific atom in the body, each atom has its own precessional frequency. To find the specific precessional frequency of hydrogen, which is the one we use in MRI, you use the Larmor equation, which has your precessional frequency equals the strength of the magnetic field times your gyromagnetic ratio. That's how you get your hydrogen atom specifically. So now you're asking, wonderful, we're able to pick out the hydrogen atom specifically. We still don't know how we get our MRI signal. Well, basically, we have to move that magnetic moment away from the external magnetic strength. How? Good question. We do that through resonance. Now, resonance is when we're adding energy to the atom. Because remember those spin down anti-parallel? They moved away from the magnetic strength. That's what we're looking for. So if you can add energy, the nucleus gains energy if the additional energy delivered is at the same frequency. Remember the Larmor frequency or the precessional frequency? So to be able, it's just like you adding apples to apples. It has to be the same for it to add frequency. So when we're adding frequency or we're adding energy, it must be at the same frequency. This additional energy is an RF pulse or radio frequency pulse. Now this is what the MRI machine can generate, is an RF pulse at the same frequency that we just found out was the hydrogen frequency. So it adds energy to that hydrogen frequency. What does it do? The added energy causes the atom to resonate. It allows the the nuclei, to oppose the main strength, the BO, and become high energy spin down nuclei, so that the net magnetic vector is now opposed to the strong magnetic external strength. Now this is a graphic representation of that. Remember, we've got our external magnet strength here. You have your spin up nuclei, but because this field we've now pumped energy into these nuclei, even though you have your external strength here, we've added energy, so now they're able to oppose the external strength. Now what does that do? When you cancel everybody out, now you have a net magnetic vector in the opposite direction. It's opposing your external magnet strength. And this is your net magnetic vector here. So you see, when you add resonance, since we know the precessional frequency of hydrogen, we can add energy or resonance into these little hydrogen atoms, which causes more to oppose the external magnetic strength. And it's that opposition that we need to be able to detect the hydrogen signal to get our MRI signal. Now, resonance creates two different things that help us to be able to see the signal in MRI. The first, as we've already kind of seen, it moves the net magnetic vector away from your external magnetic strength. And this creates what they call a flip angle. Now, this is the magnitude of this flip angle depends on the amplitude and duration of your RF pulse. What we mean by that, here is your external magnet strength. Here is your net magnetic vector. Remember, when it was pointing down, it's going opposite, opposing your strength of the external force. The difference is your flip angle. Pretty neat. You can graphically represent that to a little more understanding in that on the 90-degree angle, you've got a 90-degree flip angle. So that means you've got enough energy to take all of those net magnetic vectors that are pointing down. Now they're pointing 90 degrees. This becomes your longitudinal plane. The longitudinal plane is synonymous with your external magnetic strength. The transverse plane is down here, and that's essentially where you end up with your flip angle. These two are typically going to be at 90 degrees for each other. And there's your 90-degree flip angle. The second thing that resonance can cause, which helps us to get a signal, is the hydrogen nuclei move into phase with each other. What that means is in the same place along the precessional path. Remember the precessional path with our orange and the little dots created that circle? That's the precessional path. When they're in phase, they're on the same place on that path, which means instead of being all over the place, which is out of phase or incoherent, nice word, they make it in phase. When you add resonance, everybody's in the same place along the precessional path, which creates coherent. Now, basically, these are some of your basic ideas surrounding MRI. It's a whole lot more to it. So I hope I haven't confused you too much or made it too simple or too confusing. Let's go back to confusing. Anyway, this is Lisa. I hope you enjoyed the presentation, and we'll be back together soon.